down the second assignment. Okay. If you submit your homework 4, okay, I will try to take a look before I even have chance to finish your program assignment 1. Okay, I'll be able to give you feedback on the homework 4, which is closely related to what we try to accomplish in this project assignment. Okay, if you are anything majorly wrong or major misunderstanding about what I hope you will do, okay, I'll give you feedback before this weekend, okay, for the feedback of homework 4. So let's go to the details of this program assignment, okay. Again, you can use any platform, okay. There's no restriction on the, even if you have math libraries and things you want to use as comparison or benchmark, you're welcome to, okay. The only requirement part is that the row compressed sparse matrix, okay, that need to be implemented by yourself. Okay, but if you want to use any other tool to help you for that development, verifiable things, you're welcome to. Okay, but I would like to see the main point of this is not to produce, not like last time. Okay, the project assignment 1 is try to give you a utility you can take with you everywhere. Okay, so that's that purpose. Okay, this purpose is not that you will have your own matrix solver. No, okay. I still encourage you for later. You use the much more optimized and more than 100 man-year optimized math library by other people. Okay, so the main point of this is for you to know this is a great exercise for writing modular codes that can be tested in different ways. Okay, so this is the main point. Okay, so I will not be asking you that you will take this module around to become your standard matrix solver. If you're really doing matrix solver, please don't. Okay, because they're like the 3 things I posted. Okay, from Sandia National Lab, from NIST. Those you are looking at least more than 100 man-year behind for every part of optimization. Okay, your code is not going to be. If you can be better than that, then that's great. Okay, don't get me wrong, but it's not likely. Okay, so not the goal. But these will show you when you write a code, right, for some operations, how do you apply different redundant coding. Okay, if you have a matrix solver, you implement twice. Okay, either in different data structure or in different ways of computations, that you can come up with automated task suites that can be used to check your execution of your program developing larger and larger. The debugging things you may have learned before is, okay, you write a program and something is wrong. You know the answer is not right. Your old debugging method, okay, you are still welcome to use those, is to look at the source code carefully, load into a debugger, trace line by line, and use your hand on the side to debug. That's one way of debugging. I'm not substituting that, okay? But it is not the most useful tool when your code getting larger. Smaller code, you can do that, okay? Imagine you are in charge of even 20,000 lines of code. You cannot do that in debugger, okay? So you will rely heavily on modular testing that can be automated. Okay, whenever you write larger program, you modify the some part. You have many other parts, right? The consistency with your newly added part need to be checked by regression testing, not only by debugger. Okay, so this is the main purpose of this. Okay, that so you can learn this principle and learn to code with the testing in mind. Okay, this is a whole. If you already do that, that's great. Okay, but if you write program before without a testing strategy in mind, not a good programming technique yet. Okay, so this is to enforce that. Okay, enforce that. So that said, okay, 2 persons in the group, you are welcome. Okay, you can use your built-in exception handling from the last assignment, but it's not required. But do remember, if you use those exception handling, those checks, it takes a lot of time. Okay, so that's the when you can be turned off. Okay, if you for the debugging for exception. Okay, many times I'll tell you that your first trial should get a lot of NaN, okay? And that's coming from exceptions, okay? But the when those happen, remember those trials can be turned off, okay? So that's the because it will affect the efficiency for very large program. You should learn gradually let the standard to handle for you, okay? You can check whether the exception is causing problem, but those checks can be turned off, okay, eventually by a global define or something, okay? Okay. And as I said, that's about all the, yeah, okay. So what you're going to do is implement a matrix solver, AX equal to B, okay, for the large matrix in your homework 4 of that memory circuit, okay, about 12,000 rank, okay, solving that, okay. And you are going to solve 6 factors, okay, solve it for AX equal to B, okay, I give you 6 factors. The first one is very well conditioned, okay, and there are the second one and the last one are EO conditioned, okay. So you are actually a lot of accumulations of these precision errors will happen, okay. So this is for your test, but so that if you can use either a direct solver or iterative solver, which I'm going to show you today, okay. Iterative solver is a lot easier to code. Okay, a lot easier to code. So please gauge your time, but the convergence can be bad. Okay, just that. Okay, just as a something to tell you beforehand. Okay, if you have limited time, let's play with implement a iterative solver. It's totally fine. Okay, totally fine. And it is a lot easier to code. Okay, a direct solver with any aerial factorization and minimum filling algorithm. Even you do only partial, search and things, it's much harder to code than the iterative solver. Okay, so you look for challenge. Okay, as I said, direct solver is the default in every SPICE program. It's more reliable. Okay, if you're looking for challenge, please you can go for the direct solver. But if not, okay, then the iterative solver it's a lot easier. Okay, a lot easier if you are limited by time. Okay. And you are going to get a validation at the end for matrix solver is easy, okay? It's just that whether your solution is correct or how good is your solution can be always checked by that residual factor, okay? Whether you have done your job in that residual factor is very close to 0, okay? So that end result is can be self-validated very easily for matrix solver that this is a good thing, good example for you to implement, check in different levels, okay? So I don't have to tell you this is the correct answer, okay? Because you are going to see immediately whether you get the correct answer, okay? For large problem, these kind of things is precious, okay? Usually for large problem, you don't know, okay? You solve a nonlinear things, you don't know the answer, okay? It's very difficult to check whether you have solved it correctly. For EO condition matrix, there are multiple solutions, and sometimes even you pass that test, it's still not the solution you want. That's another domain of discussions, okay? But that's at least for this assignment, this can be easily checked, okay? And you're going to extract the memory usage and the CPU time, just like in your homework 4, okay? You can use your hand to estimate, okay, this is a significantly large matrix. So the main thing that's being handled should be by those data structures, okay? So you use your hand to estimate how many floating point operations needed and compare what is going to be reported to you. Okay, and that number for a sizable program, okay, for any toy program is just dominated by parasitics, okay, that doesn't matter. For the sizable program like this, you can define a efficiency, okay, how good is your compiler, how good is your, CPU handling this kind of job, okay, and there are linear solver are one of the most popular benchmark for compare how compiler perform. Okay, so if you go for a compiler class, say how good is your compiler, okay? They run a large linear solver, okay? And benchmark what is the efficiency both in execution and in memory usage, okay? So that's that is a bonus, okay? So not something we have really really taught in this class, but in a standard compiler course, this is one of the standard benchmark. Probably the matrix even larger than this one, okay? But this is large enough for that number to be meaningful. Okay, so yes?
Can we use like third-party libraries for memorizing the CPU time?
Please do, compare, yeah. So there's no restriction, okay? But the purpose is not to come up with your own matrix software in the future. Right? As I say, you can call another matrix software and compare with your own implementations. That's a bonus. I love that, okay? I love that. There's no restriction on that. But I need you to use this assignment to show, okay, I have a goal of this row compressed sparse matrix. How can you implement modular testing for the entire design of when you reach a software, right? So there are all the permutations, all the things to check, right? How do you check the permutation? How do you check the matrix multiplication? Individual tests for that, okay? And all the modular tests for the method you implement. The more tests, the better, okay? Okay, so I'll continue from last night. Okay, the next 3 slides are not exactly rich. Okay, it's an important principle to look at things, but it's nearly not applicable for most problems. Okay, but it's good to know why most of the solvers they do at least this part of conditioning. Okay, so if you have a matrix, if I know the inverse, right? Inverse can be derived from something called the Cramer's rule. Okay, you have learned that in your linear algebra, but you can see the Cramer's rule tell you that inverse is so expensive. Okay, totally expensive, right? You get the a sub matrix, right? Deleting the I and j row, get the determinant of that. That's still n rank n minus 1, right? And divided by the original determinant. Okay. So this is heavy, okay, heavy computations. For sure, in 2x2 or 3x3, you have closed form. That's easy, okay. But when they any sizable matrix, okay, this is usually way too expensive, okay. Unfortunately, the most rigorous definition of your matrix conditioning is by this, okay. Say if you're solving AX equal to B. You're interested in if I perturb or if the matrix element contains some errors. Does that error get amplified or get reduced? Okay? So a natural operation, you take a differential operator to this. Okay? For sure, B is a constant. So you get A delta AX, A delta X. You, after some manipulation, you will come up with this very simple equation. Okay? That means, okay, your error is amplified by the norm of your inverse matrix times the norm of the original matrix. I'm done. Okay, so this is rigorous. Okay, so the how good is the condition of your matrix can be evaluated if there is an inverse that you can compute. Compute the norm of the inverse, compute the norm of the original matrix. That 2 norms times to multiply that together is the matrix conditioning. Okay, this is entirely theoretically rigorous. Okay, but not applicable because I don't know this. Right? If I know a minus 1, then great. Right? Then I solve the whatever equation there is. Right? So this is a rigorous definition for you to think about it, but it's hard to apply. Okay, so most of the time we do the estimate just by this. Okay, there are 2 ways to get the estimate of the inverse norm. Okay, first is just that okay, the easiest norm that easiest inverse I can get is just a diagonal. I estimate it. So I only take the diagonal. Okay, maybe you do some column permutation for partial pivoting. Okay, you have the diagonal and you use that as your, because d minus 1 is easy to get, right? So, but if you do this, you just normalize your diagonal to 1. You achieve nothing else, right? So this is common, okay? But this is one of the things you constantly see people do, okay? Before you solved it, do a whatever, even it's an iterative solver or whatever solver, do some column permutation, okay, so that it's become diagonally dominant. And after that, you normalize the diagonal. That's common, okay, and easy for almost most program. You can do that, okay. Most matrix solver you can do that, okay. The second choice of your A-1 is from prior knowledge, okay. If you have some prior knowledge of that inverse matrix, either from previous solutions where you have time to solve it, like in a transient simulation, okay? That in the previous time step, you have already solved for a problem. And you have some knowledge of the solution already. And you can use that to apply for preconditioning, okay? But that prior knowledge, for sure, is out of the domain of a general linear solver. Okay, so that's prior knowledge or this, okay? This is the only two practical way, yes?
So, well, by saying you use D inverse in D, you mean you instead of kappa A, you use kappa D equals D inverse times D?
Yes, an estimate of kappa. So it's and this can be calculated, right? A norm that we have practiced just from last night. There's some at the upper bound of a given matrix. It's not hard. That's very easy to estimate, but an unknown matrix, for sure, there's nothing you can do. So I have to take an estimate for the inverse of A. And lack of anything else, then it's the diagonal. It's my best estimate, okay? Yes?
Can you use a D inverse, the norm of the D inverse times the norm of A? Or do you have to use D inverse and D?
For sure, this is what I meant, right?
Okay.
Yeah, but you know, this is not bad. This is doable, right? It's totally doable. Right? So this is the condition number. Okay. Very rough estimate of the condition number. Okay. Okay, so we give you an example. Okay, you just that. Okay, do say I was given a matrix. The first thing I do, this is typical for things that it's well conditioned, not well conditioned, and not very tricky matrix. Okay, tricky matrix doesn't mean it's not real. Okay, if you imagine that anything that can generate a chaos is by definition is an EO condition matrix, right? Because things will evolve, the error is supposed to be amplified. And there are many chaotic things in our world, okay, and those are real, okay, including how the weather flow, the the thunderstorm or twisters and tornadoes and things. Those are all EO condition, okay. The reality is EO condition, okay. So, but this is if it's not, it's a stable equation set like this. Well, this is the cheap thing I can do, okay. Column pivoting, okay, make it to be reasonably diagonally dominant and normalize to matrix conditioning by diagonal normalization. Okay, I times the D-1. So this, and then you start solving this. For this example, actually this is sufficient. The original equation you solve there with the finite precisions, you will actually get wrong answer. But if you just apply something that's simple, okay, this is already make many of the stable solutions to be solvable, okay. Okay, and if you only do this, okay, in your direct solver assignment, I'm fine, okay. Okay, so don't go for there are all these many heuristics in getting the best LU factorization, okay. Don't try it, okay. Unless you have infinite time, that's fine, okay. But probably you don't have infinite time, okay. Okay, any questions? Go to the matrix iterative solvers. So the direct solver we introduce, it is great. Okay, it's stable, and if you control the pivoting, is okay. One more things about Microsoft need better robust programming. Hate it. Sorry. Apologize. And PowerPoint actually is much smaller than Word in source code, but still have problems, okay? Okay, so let's go through, okay, their method that, or the nature of the matrix, that any of the direct solver is not possible, okay? It's just too memory intensive, or the coupling is such irregular, there's not a good trade-off between the minimal fill-in and the pivoting, okay? Usually your circuit is not like that. Usually your finite element program is not like that, okay? Because those are things. But there are things like Navier-Stokes equations known for their instability and irregularity, okay? That you simply cannot do direct solver, okay? Direct solver will lead you to that infinite loop, not infinite loop, it's a very, very large loop and cannot get any answer, okay? So iterative solver is one. Some problem just demands iterative solver. And sometimes it's easier, right? Direct solver, you only get the answer at the end. In the middle, you get nothing. If somehow things are terminated, you get absolutely nothing, okay? But iterative solver is different, okay? I'm taking a gradual approximation, try to improve my residual, right? And if the time is up, I haven't finished to the criteria, at least I give you a guess, okay? And for many control theory things, okay, the time is as important as the answer. A real-time system, right? The time is up. Give me an estimate, right? If you're doing direct solver and you are somehow that you have a trigger a pivot on the fly, and you are dead, right? Because you don't let me finish, I cannot give you an answer. Iterative solver, anytime, okay, just how many iterations I have. It's just a quality of this residual factor as long as I can guarantee that this ratio is smaller than 1. Each time I apply the iterative solver, you will improve some of the residual factor. Right? And if you ask me to terminate because of real time or something, I can give you an estimate. Okay, yes?
Oh, so like the longer you run it, just the more accurate your
if this ratio is always maintained.
Oh, okay.
There are problems for sure. All the precision, noise pollutioning that can happen in direct solver can happen here as well. And when this one it's larger than 1, for sure, you get even worse. But most of the time, actually, it's you will observe this kind of behavior. Iteration, okay, and this is the residual norm. Okay, you have something like this, where you try to get to here, and this is called the local minimum. Okay, so many times that this is more common. Okay, you apply a lot of iterations, but somehow that matrix, this factor is close to 1. You get trapped into a local minimum. Okay, but okay, so.
Convergence is until equals to 1.
Convergence you can define just on the residual factor, right? This, right? No. Convergence criteria should be for any matrix for a linear system, right? This is convergence, right? You can set a tolerance for convergence, whether my solution factor fit my system. Okay? So linear solver actually is the good thing is that you can always easy to check whether you have solved it correctly, how good you have solved it correctly. Unfortunately, this does not apply in nonlinear solvers. So nonlinear solvers, you don't know. When you nonlinear problems, when you are trapped in the local minimum, you don't know it is the true minimum or not. Okay, but in linear system you can. Okay, because this should go to 0, right? If your matrix is reasonably conditioned. Right? But nonlinear problem, then these become much harder. Okay, There's no easy way to check your answer. Okay, so now how should we find what is that T and C that can give the most highest probability that these can maintain as -1 is the goal. Okay, and you can probably imagine, okay, because linear solver has been one of the main things for all kinds of problems. This has been done by all the math genius in the 16th and 17th century. Okay. Not by now, okay? This is such an important problem. And really, many times, this is life and death, okay? And there is a time when there's no computer, right? Whoever can get the matrix solver faster will survive. Like the computer game of cannonball, okay? You are shooting cannons, right? This person adjusts the cannon in a way, okay, and I know what is the best way to converge the I hate you, right? So once they probably have the same cannon usually, and then start shooting each other in calibration, and there's an operator, seriously, computer on the side to calculate what is the next angle and things I should set. Okay, whoever can do that faster will live, right? Seriously, it's not kidding, right? So this something. So there are all these, including the ingenious Da Vinci and things, have all looked at the problem, because at the time this is life and death, right? To invent something in this domain is life and death. So, okay, so they cannot do the minimum fill in, okay, do the direct solver at the time of computer by hand, okay. They cannot do this has been exercised by all the math genius in the early days. Okay, so one of the most easy to see is by Jacobi, the Jacobi matrix Jacobi. Okay, the Italian mathematicians in the 16th century. Okay, so if you look at a system like this, okay, a system you have to solve. This is a matrix solutions. Okay, after you choose the pivot. Okay, after you choose the pivot, you move the thing to the left, okay, and then this becomes your equation, right? So it is natural to see that this is the T, right? Let me say that again. I want a X evolve according to T, okay? The natural selection of T is by the Jacobi method, right? So I do diagonal dominance, normalize it, and then I move it to this side. So each time I have an initial guess of all these x1, x2, x3, I use it to update the next factor. Okay, so this is one of the, if you continue doing this, okay, your initial guess is, I'll show you what is the initial guess. Then after, if the matrix is well conditioned, okay, you can see that this, if it's a truly diagonal dominance, after several iterations, it will converge. Okay, it's one of the main methods, okay, that you can compute, okay. Easy compute, you're going to practice it, okay. So in formulation, it's just this, okay. Jacobi iterative method is that your A has a diagonal, okay. The lower without the diagonal, okay, matrix. Upper diagonal without the diagonal, okay, the upper matrix, okay. These are minus because of these. I move things into the minus sign, okay. But the A is represented. The A is represented by D equals to D minus L minus U, okay. Exactly, okay. Exactly, okay. Just like the previous equation that I showed you. And you do this manipulation, move the L and U, these are all factors, right? Matrix time a factor, move it this way, right? So your X modification should be D minus 1, easy to get, L plus U, and this is your C, the residual factor. So this is your iteration, right? Easy to write, okay? You can do a little bit better thinking, okay, now actually I know how to get the inverse of a lower triangular matrix with the diagonal, okay? This is something that we know reasonably how to do, okay? And then I can use this to iterate, okay? Instead of just using D minus 1, okay, but I use D minus L, which is a lower triangular matrix. The inverse is not hard to get, but hard to get for sparse matrix, okay, because there's no guarantee that the inverse will be sparse at all, okay. So this is maybe doable, okay. The good thing is, okay, a long time ago it has been proved I don't need to do Gauss-Seidel. This is the Gauss, okay, the German mathematician, the genius, okay, Gauss, okay. He figured out is I don't need to even do this, okay. As long as I'm doing the Jacobi iterations, when I do my updates, okay, if I have x1, I use the updated x1. I use the updated x1 in the next evaluation. When I get x2, I use the x2 in the next evaluation. Okay. Okay. So whatever updates elements I get, I use it directly in evaluating the remaining elements. If you do that, it's symbolically the same as Gauss-Seidel. Okay. The Gauss himself figured it out. Okay. So it's not. Yeah, I don't really need that inverse. Okay, because the inverse will be still. If you have a sparse matrix, no guarantee that it's sparse still. Okay. So you don't have to do that. Okay, because I'm only interested in solving this, right? I'm only interested in this form instead of exactly what the component is here. Not something I'm interested, right? So if you apply the Jacobi iterations, but use your updated element always, then you are symbolically the same as Gauss-Seidel iterative method. That said, the convergence is governed by, in here, it's this, right? By, in convergence of Jacobi is governed by this, right? Okay, I should list it so be clear. So this, the norm of this matrix, the T matrix, right, govern the convergence. In Gauss-Seidel, is this T, this is the T in Gauss-Seidel, is the iterative matrix, right? Their norm governs how it will converge. And there's no guarantee that this norm is better. Okay, so Gauss-Seidel, depending on the applications, sometimes Jacobi is faster, sometimes Gauss-Seidel is faster. Okay? There's no guarantee, okay, for general problems, okay. If you can give me more specific problem, then I can probably prove a little bit more about what is a convergence property of each iterative solver. But there's no general conclusion, okay. These also show you another trade-off. So Gauss-Seidel looks interesting, right? Whenever I have a value, I use it to update my follow-on computations. So you come up with a better, many times a better solution. But I also introduce a data dependency, right? Before each iterations, I can do in Jacobi iterations, I can do it, every element is computed in parallel. I can't. There's no data dependency. In Gauss-Seidel, that is destroyed. That data dependency is destroyed, right? So it's a trade-off, okay? So whether it should be Jacobi or Gauss-Seidel, okay, it's really your platform-dependent answer, right? Because Jacobi is trivial to parallelize, right? When you calculate this, none of this depending on the present solution. Right, so every element can be executed simultaneously. But in the Gauss-Seidel, it's something that you have to wait for the first one to finish to calculate the second one to finish to calculate the third. Right? So there's additional data dependency. Questions?
You have to start with your initial approach.
Yes. I'll show you what is a popular initial. And in here it's clear. Right? Just this one, you start with this one is 0, right? The next iteration, this is your initial guess, right? And diagonal inverse is trivial, right?
But why is there any intuitive way to understand why does it converge? Like why would it provide more precision with every iteration?
It's how your T, right? this is how it converges. The T matrix, the estimate, right? Substitute this in and expand it out, then you can prove with a known property of the A that the Jacobi or something is convergent. That is pretty lengthy proof though. Okay, and let me tell you that you have to give a lot of constraint in order to prove that it will definitely converge. It's not an easy thing to prove.
But it does converge.
Depending on your matrix.
Yeah.
Okay. So the rule of nature usually apply if there is actually a stable solution. Then many times you can prove that even if you do something that's greedy, this is pretty greedy. Okay. Each time I want improvement, right? If you do something greedy, you will go into the valley. Okay. This is called a basin of convergence. Okay. So the stable problem, imagine that this is you are playing that marbles go into a basin of things, right? The contour of that basin is about how easy to converge. For a very well posed problem, there's only one big basin. However you start, you will converge, right? As long as you are every time you know you are making improvement, eventually you will get to the bottom. But there are many problems. The basin looks very weird, especially for nonlinear problem. To prove that I can absolutely converge, it's a very difficult thing, right? Because I need to know the entire objective function map for all the different possible x factors, right? So that is a hard proof, okay? Some proof exists, but beyond our discussions. Yes?
And then it also depends on like what your initial
Sure.
is, right?
Totally.
Like, the closer you are to like the actual x value, the faster it'll converge.
Yes,
where
totally.
if you like just like close your eyes and choose like 2 or 4.
Yes,
really random numbers,
again,
right?
back to the basin of convergence, right?
Okay.
How far you are away from that
actual
body
solution.
is for sure matters, right? And in the nonlinear solver, it will become even more important, right? Because there in the nonlinear, most linear systems, there's one solution. Right, but nonlinear solver is very easy to show that I have many local minimum. Okay, local minimum doesn't exist in this system. Okay, so it's not that bad. Okay, not that bad, right? So, but still, right? How deep is that basin, or how your initial guess will not from these pollutions of the precision errors will lead you astray. That's still possible, okay? Then you cannot get to the bottom of convergence. But for linear solver, this is not as bad as a nonlinear solver. Not as bad, okay? Yes?
And when would we stop? When would we know that the answer, we have got the final precise answer? Like,
Okay. For linear solver, this is actually easy to check, right? The validation of the quality of your solution is actually you have a good estimator. Okay, so for sure, when I teach you nonlinear solvers, okay, since I don't know there's no way I can do easy validations, so I have to introduce to you another error estimator, right? This one I don't have to introduce the error estimator we do in local analysis, because this is a very good validation. Okay, for nonlinear problem, I cannot do this. Okay. Then I'll teach you further how you can estimate the error from, I don't know the answer, okay? I don't know even how evaluating that objective function is very hard. Okay, what should I do? Okay, then but later.
The idea of to check is like to do this validation after every iteration, or like after a bunch of iterations we do this validation?
It's common you do it. This you do iterative solver. This is common to print out for you to check, right? Check your solution each iterations. You check the how much improvement difference has been made, and what is your residual factor at the present time. So this very simple report will tell you how good is your iterative solver indeed. Any other questions? Right. This is for sure. We haven't reached there yet. Okay. Any other questions? Okay, play it. Okay, so this is actually, if you have the just the homework 4 routines, okay, Jacobi software should be 4 or 5 lines. Okay, everything is there. There's not really nothing is not there. Okay, this is, so let's try. Okay, so Jacobi iterations. Okay, this is your initial guess. Okay, see if you can achieve your 10 to the minus 7. Okay, Jacobi iterations. Okay, this you have the matrix as from before, so really just this. Okay, yeah, constructing this matrix and do the iterations according to this. That contains a this is nothing but the diagonal inverse, right? You know what is L plus U, right? L plus U, create a matrix that's the get rid of the diagonal of the matrix. Do this, okay, and iterate on it. That's how simple iterative software can be constructed. And you can also see that if you only have pen and paper, okay, it's not bad. Not bad at all. For sure, the inverse rule, d times d minus 1 has to be the unity, right? So that's how it can be proved.
Oh. Should reduce as you do more iterations, right?
Yes. You should. After you
No, it's increasing.
increasing. Yeah, okay. So that's okay, we'll trace it out. Okay, something. Anybody get a decreasing norm? No. Okay. Well, figure it out. Okay, how to make it converge. But the Argand asked just a question. Okay, I hope that to make sure. I have said this before, but maybe it's that time you don't have, first time you hear about it, don't know what I mean, okay? When you do programs, okay, you need to learn both programming styles. One is a very rigorous thought that design your modules, and every module need to be tested in the most efficient data structure, okay? It is also very important for any programmer to know the hacker practice, that you can solve a problem in the most reliable but fastest way. Okay, you can write whatever data structure, doesn't matter. Okay, it is not only useful in the interview or you're going for Hacking New York competition that you will get. Okay, if you're really serious about a software job, okay, all the software headhunters is in all these hacking events. Okay, if you're serious about getting into Google or Facebook and things, so the easiest way is not to knock on their doors, but make yourself go to one of the hacking competitions. There's Hacking New York, there's Hacking Pittsburgh, there's hacking whatsoever. Okay, just search on Google. There are all these annual hacking events where a application was given. Okay. And the door is closed. Okay, whoever can deliver the solutions in 2 days will win the prize, grand prize. Okay, and all the headhunters there. Okay, so that's the thing. But more importantly, the hacker practice is when you debugging, you write small program for the function you are debugging. And trust me that when you get older, or even when you get more source code, that's your responsibility. Your attention span is not infinite. You have to be able to finish the test the soonest possible. And that is similar to this practice, okay? So cultivate that habit, okay? That's something that as a long-term programmer is a must capabilities that you will be able to do both mode. Careful planning, that you can go back to the source code again and again, figure out efficiency and things. That's one mode. The other is hacker mode. Okay, hacker mode to write small test program along the way when you're dealing with a large program. Okay, both are needed. Okay, and this one is even more needed when you get to my age. The attention span is like 10 seconds. Okay, so I have to figure things out quickly. Okay. 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 There's one more iterative method. Okay, but I'll not. I'll finish that next Friday. Okay, but I don't expect you to implement SOR. Okay, the selection of that parameter is harder to determine. Okay, but so if you write your program assignment 2 in iterative solver, either Jacobi or Gauss Seidel. Okay.
So D inverse B is a good first guess for X always.
No.
For this.
There can be better guess. Can be. Okay. But this is if you there's no prior knowledge or no whatsoever. This is the only thing you have in Jacobi method. Right? So what is my initial guess of SK? The first one, X0 or 0. Because that's the only information I have. And that gives you the first iteration D inverse B. If you have any prior knowledge, right? Any prior knowledge, you should use that as the X0. Right? Nothing but this, right? D inverse B is assuming this is a 0 factor. If you have any prior knowledge of the solution, you should use that as this one. And then that will start your iterations.